Welcome back to the Deep Dive.
Good to be here.
So today, we've got something, well, really unexpected lined up.
A real, you might say, collision of ideas spanning centuries.
Exactly. We're talking ancient Greek philosophy, like right up against cutting-edge quantum physics. It sounds almost paradoxical itself.
It really does. But the connection is surprisingly strong.
And that's our mission for this deep dive, right? To unpack how a concept from, 2,500 years ago,
Not that, yeah.
how that idea is echoing in some of the most advanced science happening today.
Precisely. We're going back to Zenon of Elea, 5th century BC.
Okay, Zenon, wasn't he a student of Parmenides?
That's the one. And Parmenides had this radical idea that change, motion, it's all an illusion. Reality is fundamentally static.
Wow. That's a heavy concept, hard to wrap your head around.
Definitely. And Zenon, to support this, came up with his famous paradoxes. You've probably heard of them.
Like Achilles and the tortoise.
That's one. And the other key one for us is the arrow paradox, the arrow that never actually moves.
Right. Because at any instant,
Yeah.
it's just there.
Exactly. These weren't just throwaway thoughts either. Plato wrote them down, so they stuck around.
Okay, so that's the ancient side. Now, fast forward, a long way forward.
To quantum physics. And there's this phenomenon called the Quantum Zeno Effect.
The Zeno Effect, named after it.
Named directly after him, yes. And get this, it basically says if you observe a quantum system often enough, frequently enough, you can actually stop it from changing. It just stays locked in whatever state you first found it in.
Wait, hold on. Just by looking at it, that can't be right. If I watch a kettle, it still boils.
Well, yes, in our macroscopic world, that's true. Observation seems passive. But down at the quantum scale, it's a whole different ballgame. Observation isn't passive at all. The act of measuring does something.
It really makes you question what observation even is at that level, doesn't it?
It absolutely does. And the really amazing part, this quantum Zeno effect isn't just some, theoretical curiosity anymore.
It's real, like lab tested.
Oh, yeah. It started as theory, but now it's actually become a practical tool. Scientists are using it.
Using it for what?
To control and manipulate these super delicate quantum systems. It's actually crucial for building things like quantum computers, advanced sensors, secure communication.
So a 2,500-year-old philosophical puzzle is now helping build futuristic technology. That's wild.
It is pretty mind-bending when you think about it that way.
Okay, let's dig into this. Starting with Zenon. Tell us more about that arrow paradox. How did he argue it?
Okay, so imagine an arrow flying through the air. Zenon says, let's freeze time at one single indivisible instant.
Like hitting pause on a video.
Exactly. At that frozen instant, where is the arrow?
Well, it's at a specific spot, not moving in that instant.
Precisely. It occupies a space equal to itself. It's at rest.
Okay.
Now, if time is just a series of these instants, and in every single one the arrow is at rest...
And where does the motion come from?
Ah, I see.
He's saying motion itself must be the illusion.
That was his argument. It's built from moments of stillness, so it can't be real motion.
It definitely messes with your intuition.
Yeah.
So how does this seemingly logical trap connect to the quantum world? Is it the series of instants idea?
That's the core of the connection. Continuous observation in the Quantum Zeno Effect is like taking those continuous snapshots of Zenon's arrow.
Ah, okay. So each time you measure the quantum system,
you force it into a definite state, just like freezing the arrow forces it into a definite position at that instant.
And if you do it fast enough, before it can change.
Exactly. You keep forcing it back into that state over and over. It doesn't get the chance to evolve naturally into something else.
It's like you're constantly interrupting its process.
You could put it that way. The continuous looking, the measurement, effectively freezes it in place, in its initial state.
That's a really powerful parallel. The system is caught in the spotlight, unable to move. Now, you mentioned this idea wasn't totally out of the blue in physics when it got its name.
Right. People like Alan Turing, believe it or not.
The computer pioneer.
The very same. And the mathematician John von Neumann. Back in the 50s, they sort of hinted at related ideas, but it wasn't formalized.
Until later.
Until 1977. Two physicists, Bedianath Misra and George Sudarshan, really nailed down the theory and coined the term Quantum Zeno Effect.
Misra and Sudarshan, 77.
Got it.
And you said it's been seen in labs.
Oh, definitely. It's not just math on a blackboard. They've observed it in trapped ions, which are like single atoms held by fields. In superconducting qubits, those are the building blocks for many quantum computers. Even in single atoms interacting with light in special mirrors, optical cavities.
So it's a well-established experimental fact now, which brings us back to observation. You said measurement isn't passive in quantum mechanics. Let's unpack that a bit more.
Yeah, this is crucial. In our everyday world, classical physics, looking at a bowling ball rolling doesn't change how it rolls right.
Right. Maybe the light reflecting off it pushes it infinitesimally, but nothing we'd ever notice.
Exactly. But quantum mechanics, totally different. Measurement is invasive.
Invasive how?
Before you measure a quantum system, it can exist in a kind of fuzzy state of multiple possibilities at once. A superposition.
Like Schrodinger's cat being both alive and dead.
Kind of like that, yes. But when you measure it, say, you measure its position or energy, you force it to choose one specific outcome. The fuzziness disappears.
That's the wave function collapse ideal.
That's the term, yeah. The measurement collapses all those possibilities down into one single reality that you observe.
Okay, so measurement forces a choice. How does doing that repeatedly stop it changing, like in the Zeno effect?
Well, imagine the system wants to naturally evolve from state A to state B over some time.
Okay.
But if you measure it very, very frequently, much faster than the time it takes to get from A to B, each time you measure it, if it's still mostly in state A, the measurement forces it back into being fully in state A. It resets the evolution process.
It's like trying to climb a ladder, but every time you lift your foot, someone pushes you back to the bottom rung.
That's a great analogy. You keep interrupting the progression. You tap the swing lightly and often it never gets going. Frequent measurements prevent the system from making the transition.
And just to stress again, this is purely a quantum thing. My watching a plant grow doesn't stop it growing.
Absolutely no classical analog whatsoever. Observation in our world doesn't fundamentally alter behavior like this.
But down there, the observer is part of the system, in a way.
You could say that. The interaction is unavoidable and has real consequences. And like we said, experiments confirm this. They can literally inhibit quantum transitions by watching closely.
Incredible. Okay, so let's talk applications. Quantum computing seems like a major one. How does Zeno help there?
Well, the heart of a quantum computer is the qubit, right?
Right. Can be 0, 1, or both at once superposition. That's where the power comes from.
Exactly. But that both at once state, that quantum coherence, is incredibly fragile.
Fragile how?
It's easily disturbed by almost anything, tiny vibrations, stray electromagnetic fields, bits of heat, basically noise from the environment.
And that causes errors.
It causes decoherence. The qubit loses its quantum bothness and collapses into just a regular 0 or 1, like a classical bit. That kills the computation. It's a massive headache for building quantum computers.
Okay, so decoherence is the enemy. How does the Zeno effect fight it?
The idea is, if you can frequently measure the qubit in a way that checks if it's still in the desired quantum state, without fully destroying the computation, you can keep forcing it back into that state if it starts to drift because of noise. It's like constantly nudging it back on track.
So you're using measurement not to read the answer, but to protect the state during the calculation.
Exactly. It's a form of quantum error correction, or rather error prevention. You're actively suppressing the decoherence pathways by watching.
That's clever. Using the weirdness of quantum measurement to fight the other weirdness of decoherence.
It is. And it doesn't just protect the qubits sitting there. It can also help make the quantum logic gates, the operations you perform on qubits, more robust.
Also,
by carefully timing measurements during the gate operation, you can sort of steer the qubit's evolution, making the gate less likely to fail due to errors. It improves reliability.
So Zeno is helping make quantum computers more stable and less error-prone. That's huge.
It's definitely a promising avenue, yes. One of several strategies, but an important one.
You also mentioned broader applications beyond computing, controlling quantum states generally.
That's right. The Zeno effect gives us a handle, a control knob, on how quantum systems evolve. Or rather, how they don't evolve.
Can you give an example?
Sure. Think about Rydberg atoms. These are atoms where an electron is kicked way up into a very high energy level.
Okay, super excited atoms.
Very excited and very sensitive. You can use microwave fields or radio frequency pulses to interact with them.
Right.
Now, by applying these fields in specific ways, combined with Zeno-like measurements or interactions, you can effectively restrict the electron. You can say, okay, you can only be in the small group of high energy states, not those ones.
So you're carving out allowed zones within the atom's possible states, using observation and field.
Precisely. You're engineering the state space. You can confine the system to a Zeno subspace, preventing it from exploring other possibilities.
And why would you want to do that? What's the use?
Well, this kind of fine-grained control lets you create really complex, tailored quantum states. And those are useful for lots of things.
Like
quantum simulation, using controllable quantum systems, like these atoms, to model other complex quantum phenomena, maybe in material science or chemistry.
Okay.
Quantum metrology, making ultra-precise measurements, say, of time or magnetic fields, using the sensitivity of these engineered states.
Right, pushing measurement limits.
And secure quantum communication.
Yeah.
Building systems where the laws of quantum mechanics guarantee security, having precise control over the quantum states is key.
So it all falls under this umbrella of quantum state engineering.
Exactly. Designing and building specific quantum states on demand. The Zeno effect is one powerful technique in that growing toolbox.
It really seems like a fundamental tool then.
Yeah.
But just when I thought I was getting it, you mentioned an anti-Zeno effect. What on earth is that?
Haha, yeah. Just when you think observation always freezes things, sometimes it does the opposite.
The opposite. So more observation makes it change faster?
In certain situations, yes. Frequent measurements can actually accelerate the evolution of a quantum system away from its initial state.
Okay, my brain hurts again. How can it be both? Freezing and accelerating. What decides?
It depends on the details. Things like the exact frequency of the measurements, how strong the measurement interaction is, and crucially, how the system interacts with its environment. The specific way it decays or evolves when not being watched. It's a more complex interplay.
So it's not a simple on-off switch, the context matters.
Very much so.
Why?
The nature of the system's coupling to the measuring device and the environment dictates whether you get the Zeno freezing or the anti-Zeno acceleration.
And I assume this anti-Zeno thing isn't just a weird quirk either. It has potential uses.
Potentially, yes. For instance, in quantum chemistry, people are exploring if you could use carefully timed measurements, the anti-Zeno effect, to deliberately speed up certain desired chemical reactions.
Like a catalyst, but using observation.
Something like that. Or maybe control energy transfer in molecules. It opens up different possibilities for control.
Wow. So we need to understand both sides of this coin, how to freeze things and how to speed them up using measurement.
Absolutely. Mastering both the Zeno and anti-Zeno effects is probably going to be vital for really advancing quantum technologies across the board, and of course, just for fundamentally understanding how quantum mechanics works.
This has been, absolutely fascinating. Taking us from a 2,500-year-old thought experiment about an arrow
to the cutting edge of controlling quantum bits and atoms.
Right. And the core idea, the Zenon's paradox, finds this weird echo in the Quantum Zeno Effect, where looking too closely, too often, can literally stop something from changing.
It's a powerful counterintuitive concept. That observation isn't just passive reporting, it's active participation, at least at that level.
A perfect summary. And it really does leave you wondering, doesn't it? Which leads to our final thought for our listeners.
Yeah.
Could it be that our very act of observing the universe, fundamentally measuring it, is somehow subtly influencing how it evolves? Are we, just by looking, nudging the course of reality in ways we're only starting to grasp?
Echoing Zenon's challenge all over again.
Exactly. Is our perception, our measurement, intrinsically linked to the unfolding of reality itself? Something profound to think about.
Definitely food for thought.
Thanks for diving deep with us today.